Have you ever just stopped to think about it? How microscopic electrical charges sitting on a tiny piece of silicon can somehow store your favorite songs, display these incredibly complex images, and perform advanced math faster than you can even blink? Honestly, it feels a bit like magic, doesn't it? But actually, it's just pure, brilliant logic. Welcome to today's Explainer. We're going to completely demystify the foundation of computing. We'll explore how simple switches, literally just turning on and off, scale up to create the massive, rich digital experiences we interact with every single day.
Okay, let's just dive right into our roadmap for today. We'll be looking at 1. The language of computers, 2. Hexadecimal, which is basically the human shortcut, 3. Binary math and overflows, 4. The two's complement system, 5. Decoding text, sound, and images, and finally 6. Measuring digital storage. Let's get right into it.
So, Section 1. The language of computers, from fingers to transistors. We're starting our journey at the absolute lowest level of computing hardware today.
Now, humans have used a base 10 system, also known as denary, for thousands of years. Why? Well, probably because we started out counting on our 10 fingers, right? We use the digits 0 through 9. But a computer doesn't have hands. Its brain is made of millions of microscopic components, like transistors and logic gates. And these physical hardware components really only understand two physical states, an electrical charge being either on or off. We represent on with a 1 and off with a 0. That's a base 2 system, or as you probably know it, binary.
So, you might be wondering, how do we actually translate our human numbers into computer language? To speak the computer's language, we use the surprisingly simple divide by 2 method. You basically take any normal base 10 number, divide it by 2, and note the remainder, which, by the way, will always be either a 0 or a 1. Then you take that new answer, divide by 2 again, and note that remainder. You just keep doing this until you hit 0. Finally, you read all those remainders backwards, from your last calculation up to your first, to build your binary sequence. Pretty cool, right?
And to translate back to human numbers, we use a place value chart. What's really fascinating here is how this mirrors our own math. In base 10, our columns are ones, tens, hundreds, thousands. They just multiply by 10. But in base 2, binary, each position simply doubles the one to its right. So, starting from the right, our columns are 1, 2, 4, 8, 16, 32, 64, and 128. If a computer sees the binary sequence 1-0-0-1-1, it just adds the columns that are turned on. That's 116, no 8s, no 4s, 1, 2, and 1, 1. 16 plus 2 plus 1 equals 19. It's just incredibly elegant.
Moving on to Section 2. Hexadecimal, the human shortcut. Let's see how we make long, messy strings of binary actually readable for us humans. Because let's face it, staring at thousands of ones and zeros is a guaranteed headache.
Enter hexadecimal. Hexadecimal is a base 16 system, and it acts as a massive shortcut for computer scientists. It begins exactly like our normal counting system, using 0 through 9, but because it needs 16 distinct symbols, it actually borrows from the alphabet. It uses A, B, C, D, E, and F to represent 10 through 15. The real magic here is that a single hexadecimal character perfectly represents exactly 4 binary bits, which, fun fact, is called a nibble. 2 hex characters perfectly represent a full 8-bit byte. It compresses the visual information we have to read, making life way easier.
So the crucial point to take away here is that hexadecimals aren't just some abstract math concept. You interact with them constantly. If you've ever built a website or messed around with design, those HTML color codes, that's hexadecimal. The MAC address physically identifying the exact device you're watching this on right now, written in hex. It's used in IPv6 web routing, and yeah, even in those pesky error codes your operating system throws at you when something inevitably crashes.
All right, Section 3, binary math and overflows. We know how to read binary now, but what does the computer actually do with it? Let's take a look.
It's totally fascinating how computers perform math using just these simple ones and zeros. Honestly, binary addition looks exactly like the grade school math you're already used to. You stack the numbers and add the columns, starting from the right. The only rule you have to remember is that you only have zeros and ones to work with. So if a column adds up to 2, meaning 1 plus 1, you write down a 0 and just carry over a 1 to the next column. It's perfectly logical.
But here is where we hit reality. Hardware has physical limits. A register inside a CPU has a strict set size. If we have a standard 8-bit register, 255 is the absolute maximum denary number it can hold.
That's just 8 ones in a row. You can't go higher than that in an 8-bit space.
Yeah, CPUs do multiplication and division through something called a binary shift. By shifting all the binary digits one place to the left, a CPU multiplies the number by 2. Shifting right divides it by 2. But what do you think happens if you try to add 1 to 255 or shift a bit right off the edge of that physical 8-bit register? Well, it causes what's called an overflow error. The computer literally just drops the extra digit because it physically has nowhere to store it. You lose your data precision and your system might even crash.
On to Section 4, the 2's complement system. We've totally mastered positive numbers and basic math, but let's throw a wrench in the works.
Think about this for a second. If a CPU hardware register literally only understands an electric charge as on or off, how on earth can it possibly comprehend a negative number? I mean, there's no physical state for minus, right? The solution they came up with is just incredibly clever. It's called 2's complement. We simply tell the processor to sacrifice our largest column, the furthest left bit, and completely change its job. So instead of representing a big value like 128, it now acts purely as a sign bit. If that furthest left bit is a 0, the computer knows the number is positive. If it's a 1, it knows the number is negative. Simple as that.
And to actually create a negative number, the computer performs this really neat 3-step trick. First, it looks at the positive version of the number. Second, it flips every single bit to its exact opposite, so turning 1s into 0s and 0s into 1s. Finally, it just adds 1 to that new sequence. And boom, the CPU can now successfully process negative mathematics without ever needing a minus sign.
Which brings us to Section 5, decoding text, sound, and images. Now we finally reach the macro level, where these invisible numbers magically transform into the media we interact with every single day.
Let's start with text. Early computers used a system called ASCII, which only allowed 128 characters. That was barely enough for English letters and some basic punctuation. But today, we use Unicode. Because Unicode is 16-bit, it unlocks over 65,000 unique characters. That is a massive upgrade. It allows our devices to universally display Arabic, Chinese, Russian, and yes, it's the exact reason why we can send thousands of different emojis to our friends. But what about your favorite song, or an explainer just like this one? To process sound, a microphone captures an analog sound wave. Then, software samples the amplitude or the height of that wave thousands of times a second. Each one of those little slices is converted into a binary number. The more samples taken per second, which you might know as the Hertz rate, the higher the audio quality. And think of an image as just a giant grid of tiny squares called pixels. Simple binary codes map directly to those colors. In a basic 1-bit image, a 0 is a white pixel and a 1 is a black pixel. Add more bits per pixel, what we call color depth, and you can map millions of colors. Literally every photo on your phone is just a massive grid of binary numbers telling the screen exactly what color to shine in that exact spot.
And our final section, Section 6, measuring digital storage. Because at the end of the day, all this text, sound, and imagery requires physical storage space on our devices.
Every time you save a file, you're taking up space measured in bits and bytes. We start from a single bit. 8 bits make up a byte. But here is something most people actually don't know. Because computers run on base 2 binary, storage scales up by multiples of 1024, not an even 1000. So 1024 bytes make a kibibyte. 1024 kibibytes make a mebibyte, and it just scales all the way up to gigabytes, tebibytes, and beyond.
And because it's all just math, you can actually calculate exactly how much storage a picture will take up using this simple 4-part formula. First, you multiply the horizontal pixels by the vertical pixels to get the total number of dots. Then, multiply that by the color depth to find the total bits. From there, you just divide by 8 to convert it to bytes, and finally divide by 1024 to get your final file size in kibibytes. Pretty straightforward when you break it down.
Wow, we've covered a ton of ground today, right? From microscopic transistors all the way to the mathematics of memory. So I want to leave you with this final thought. Take a look at your screen right now. Everything you're seeing and hearing in this explainer, every single color, every sound of my voice, every letter on this slide is just a massive, high-speed calculation of ones and zeros happening millions of times a second. Once you realize that, it completely changes how you look at the digital world. Thank you so much for joining me on this journey into the architecture of computing. Keep wondering,
Keep learning, and I'll catch you in the next explainer.